This is a talk by Daniel Waxman. He used to be our treasurer in the math club. Now he's a grad student studying electrical engineering, kind of with a focus on AI and like machine learning and statistics. We'll be talking about Markov chains, and he knows a lot more about it than I do, so why don't you take it away?
Sure. Thank you. Yeah, so, yeah, it works. Okay, cool. Oops, little. Am I going in the wrong direction? Never mind. All right, figured it out. Okay, yeah, so today I want to talk about Markov chains and my favorite algorithm in statistical computing in general called the Metropolis-Hastings algorithm. So a little bit about me. You can think of it as sort of disclaimers. I graduated in 2021 with a bachelor's in math and AMS. I was on the e-board of math club back then, like Adam said. So it's really nice to be back. And now I'm a graduate student in electrical engineering, doing lots of statistics. And so these are all my coworkers. It's really nice to be able to do mathy things inside of engineering and have a unique perspective on them. And then the last thing is I enjoy long walks on the beach. So now then for today, I want to finish by talking about the Metropolis-Hastings algorithm, and sort of to work backwards. In order to talk about that, we need to talk about Markov chains, further back, some motivations for why we care about this in the first place, and then to even talk about the motivations, a little bit of probability. These are some nice references that I used while writing this and while learning all of this stuff. If any of you want any of these later, let me know. So I guess first, I could just ask, how many of you have actually done any probability before? Okay, sweet. So decent number of you. I'm going to go through like the content of probably a lecture and a half in about 10 minutes. So if you have any questions, feel free to interrupt. Don't worry about being shaken into them. So for some intuition behind probability measures, intuitively we tend to think about probability as how likely something is. We're measuring how likely something is. To do this, we specify some list of all possible events. We call that omega, or the sample space, and assign probabilities to specific events. So we go to write it down, it's a lot of notation so you can keep track. So this is the sample space. So for example, the probability of rolling a die and getting a 2 is 1/6. Or the probability of rolling a die and getting an even number is 1/2 with some assumption that the die is fair. So if we want to make this in some mathematical notation, we write down a probability measure. I like to use this Blackboard font 8. So this is a probability measure. The probability measure takes in some event, which is a subset of omega, and it gives you out some probability of number between 0 and 1. Now, if we want to define probability measures, there's a few more properties that we want it to satisfy. So if we want to axiomatically define these things, we want that the probability of all events is 1. So the probability of omega should be 1. The probability of two disjoint events should be the sum of their probabilities. So rolling a 2 or rolling a 4, probability of either of them is the probability of 2 plus the probability of 4. And then a probability should lie in the interval 0, 1. So again, just translating this into mathematical notation, we have that the probability of omega, of anything happening, is 1. We have that the probability over some union of disjoint events, so disjoint means that the intersection is empty, is the sum of the probabilities. And then finally, we can't be less than 0% sure or more than 100% sure. So for any event A, P of A should lie between 0 and 1. Is there any questions about any of that? Okay, cool. If we wanted to go for a more formal definition, we have to be careful about the domain of a probability measure. And this is really not important for us to know, but I figured I'd keep it in here just in case any of you have taken measure theory or are kind of interested in this. For things to work nicely, we have to define a sigma algebra, so we call this F. This is a subset of the power set. And then usually in probability, we take the Borel sigma algebra. So we specify a topology on omega, and then take the sigma algebra generated by open sets. And then combining all of these together, a probability space is then defined by a tuple. So it's omega, the sigma algebra, and the probability measure. So no, probability measures are great. They give us a way to measure the probability of some abstract event, but this is often not what we really care about. Random variables, on the other hand, are what we care about. These are functions of events, and might be things like the sum of two dice instead of just the result of two dice. So for example, if we throw two dice, then omega, the sample set, is 1, 2, 3, 4, 5, 6 squared, right? So you have the result of row 1 and the result of row 2. This is a probability measure, or the probability measure would go from this set, the 1, 2, 3, 4, 5, 6 squared to 1, to 0, 1, rather. But a random variable such as the sum of two dice would be a real function instead. So if I wanted to analyze the odds of winning at Yahtzee or something, I'd want something that looks a little bit more like this than the probability measure. So now how do we combine the probability measure and this idea of a random variable to say how likely rolling two dice and getting a 4 is? If the random variables are discrete, meaning that they're countable at most, we can simply talk about the probability mass function. And this just says how likely any given random variable is, or any given value of a random variable is. So for example, this is something called a binomial random variable. It says if we flip a coin a certain number of times and count the number of heads, if we flipped it 10 times, we get 5 heads about 25% of the time. Very unlikely to get 0 heads or 10 heads. Now, if we want to write this in mathematical notation again, what we do is we collect all of the events such that x is equal to little x, and then take the probability of that event. Again, continuous random variables mess us up. They're a little bit harder to deal with, but not too terrible. They end up being more difficult because the probability of any single event is actually 0. Now, we can think about why this is. We can think about why this is with like a dartboard example. So if you imagine throwing a dart at a dartboard, there's certainly a non-zero probability that you get a bullseye or get in the outermost ring or something like that. But we can't really think of a way of summing all of the continuum together, right? If you do that, you either go to infinity or you go to 0. And so we actually have to think about something called densities instead. So a probability density function is a local version of a probability mass function. So we have a continuous random variable. What p of x is actually saying is how likely we are to be in some small neighborhood around a point. So if this is x, then p of x is saying how likely we are to be in an infinitesimal neighborhood. Are there any questions based off of any of that? Sweet. So one more thing about random variables is expectations. This will become important later on. They're really the main thing that we want to be able to mimic and approximate. Summaries of random variables are usually given in expectations, and these are some sort of weighted average. So, for example, the average is an expected value. We have some distribution p and some function h, then the expected value of h of x with respect to some distribution p of x is this right here. So we read it as the expected value with respect to a distribution p of x of the function h of x. You can really think about this as the value that we get on average. So this is the value that h of x would take if we drew, on average, if we took a lot of different values of x. So this is an integral or a really large sum. In the discrete random variable case, we have a sum over all x, where we take the value of h of x and weight it by its probability. And in the continuous case, this turns into an integral instead. A major part about doing rigorous probability theory is that this isn't quite sure. There's some assumptions here, but it's good enough for us right now. So some common expectations include things like the mean. The mean is the expected value of x. Or something else you might have heard of is the variance. So the variance measures how spread out your distribution is, and it's the expected value of x minus the mean squared. In general, like I said before, we can think about the expected value of h of x as like the average value that h of x takes on. Okay, so any questions on any of that? Cool. So one final thing that I want to talk about for probability is conditional probabilities. Here we're asking, what is the probability of some event A, given knowledge that a different event B occurred? And to reword a little bit, we can say, out of all the situations where B happens, how often does A also occur? So if we, again, writing this in mathematical notation, we have the probability of A given B is the probability that both of them happen normalized by the probability that B happens. So the simplest example that everybody gives ever in every textbook, in every lecture, is what's the probability of rolling a 2? What's the probability of rolling a 2 given the knowledge that the roll is even if you throw a fair die? So here, A would be 2, the set of 2, and B would be the set 2, 4, 6. So A intersect B would be 2, and that's 1, 6. And the probability of B, like we said before, is just 1/2. So we can divide 1, 6 by 1/2, and we get 1/3 as a result. This kind of aligns with what we may think, right? So if you think about taking the sample space that we had before and refining it by whenever B occurs and then counting up in that case. So here's a pictorial example that gets by the same thing. So if we consider the sum of 2 dice, so we roll 2 and take the sum of roll 1 and roll 2, then we can ask what is the probability of the sum being 4 given knowledge that the first row was an odd number. So over here, on the top, I have the first roll value, and on the y-axis, I have the second roll value. So in the red are things that are excluded from our refined state space because they don't correspond to the event B. In the yellow are things that are in our refined state space, and in green are the things that occur in both. It's the intersection. So any questions based off of any of that probability? Sweet. Okay, so now we can talk about some motivations to talk about Markov chains or Markov Chain Monte Carlo. The first one, the one that I'm mainly interested in, is Bayesian Statistics. So statistics is all about taking a model, some guess at how reality works, and then trying to describe data that you get in a coherent way. Test your model and see how your theory aligns with reality. So what we'll do is we'll call the data that we receive x, and then our model is parameterized by some parameters theta. We have two main choices if we're doing statistics. We can say that the data x is random, and then we have some fixed theta, some given value of theta that is totally true for the system. Or we can do the other thing. We can say that theta is random, we capture some uncertainty about the system, and then x is some black box that comes out of the random variable theta and the model. If we choose theta to be random, then we're being Bayesian. This is Bayesian statistics, and there's plenty of philosophical reasons, and even mathematical reasons to do this, to care about it, and to prefer this over the more classical methods that are unfortunately not really the topic of this talk, but if you want to chat about it, let me know. I'd be happy to. A big plus is that if theta is random, this is a natural way to capture prior information. So if we want to, again, roll a die, and we have some prior information that the die is fair, then we can incorporate that into guesses. So if you're being sure that theta is completely fixed, then you might think that you're never going to roll a 3 if you rolled a 1 and 2 the first 2 times. But if you have some prior information that the die should be fair, then you're more likely to guess that you'll get a 3 next time. So normally, we still specify the model in terms of what's called the likelihood, P of x, given theta. So just to say a little bit more about this term, this is really capturing the mechanism of our model. We get some data, and we say how likely it is for any given value of theta. We can transform this into a posterior, the guess about how theta looks after seeing data using Bayes' rule. So Bayes' rule is over here. You have a posterior, P of theta given x. And this is just some simple algebra that I'm not really showing, but you end up saying that P of this likelihood, P of x given theta, times the prior information, P of theta, normalized by the integral gives you the posterior. Now the main question here, if you're doing Bayesian statistics computationally, is how the heck do you compute this? This is really hard for pretty much anything non-trivial. You can think about normals, and this works out okay if you're only considering normals, but the second you get to something slightly exotic, you really have to numerically approximate this. And really, this normalizing constant is not the only thing that we have to approximate. Like I said before, really, if you're concerned about what value a function takes on average, we want to calculate an expectation. So there's expectations literally everywhere, and they're really kind of the thing that you want if you're doing computational statistics. So these are themselves kind of tricky integrals. We have the expected value of h of x is equal to this integral. So it's the integral of h of x, p of x, dx. And if just calculating the expectation on the last slide is difficult, this can get even harder and even messier really, really quickly. So this can include summary statistics like a mean or a variance, which are kind of standard things that we want. They're things that you read if you're doing statistics in high school. But really, anything that we'd ever want, including a mean, a variance, how far a particle travels on average, how spread out a particle is on average. These are all things that you'd want to calculate an expectation for. Okay. So I should mention that I have 3 different motivations here. And it's not really imperative that you understand any given one, but I'm just trying to kind of motivate why you care about the methods later. So if any of them are familiar to you, that's great. You don't really need the other ones. But MCMC was actually born in statistical mechanics, and they have plenty of terrible integrals to do that are no fun to do by hand, if not impossible. This is where Monte Carlo was invented back in Los Alamos National Lab, right around World War II. So things like how long does a particle travel on average, or even just how do we simulate this interacting system that ends up being really complex, are impossible analytically if you try to write down some system with more than a few particles for any more than a few time steps. You just end up with combinatorial explosions. Naive methods for approximating this can work well. So there are simple approximations that you can make analytically. There are simple approximations that you can make numerically. These might get you an answer. But again, if you're making nuclear bombs or something, the answer might not be good enough. Or even more relevantly, if you're making public health decisions, you kind of want to know that your answer is accurate if you're making policy decisions. So a simple model in statistical mechanics is an Ising model. And this is all about spin systems. So this is a particularly common thing to analyze in statistical mechanics and in pure math. And physically what it is describing is ferromagnetic material. So if you have particles with spin, what happens in a certain type of magnet is the particles like to align with each other. So they all spin up, and you get a net moment, and that's what holds magnets together. A way that you can approximate this is called an Ising model. where you think about the proclivity that particles like to spin aligned with their neighbors or anti-aligned with their neighbors, and take that all into account and solve some statistical mechanics with it. So the particles tend to want to align or anti-align depending on the material and their arrangement, and actually simulating this can be quite difficult. So we consider only locally, there are only local interactions, and it still ends up being impossible analytically. So what we do here is we take some energy, so energy is h of x, and it corresponds up to some constant by how the spin being aligned or anti-aligned. And then we have some Boltzmann statistics. So we put a Boltzmann distribution on the energy, with beta being a temperature, and then say how likely some given state or arrangement is based off of this distribution right here. So that denominator should look somewhat familiar because we have another normalizing constant that's pretty much impossible to calculate analytically. There's just too many states for us to add together. I guess I also wrote it down. Usually we call that Z. So it's I don't like the font that they use here, but Z. So in pure math, there's also reasons to care about this sort of thing. I think the department actually just hired a professor that does lots of this stuff for mixing times and random walks. So again, I'm not a mathematician now in engineering, but sorry, I can't speak fully, but mathematicians tend to like random walks. They're important for dynamics and just kind of interesting elements in their own right. So here's a type of random walk that we can think about with MCMC. So right here, I'm just simulating some particles that go up or down at each time step, and which hit some boundary and then have to be reflected. We keep them within a certain range. Another thing that is somewhat involved to explain, but really one of the main reasons why pure mathematicians seem to care about MCMC is with graph colorings. So you call something a proper coloring of a graph if you're able to use different colors such that none of the neighboring nodes share a color. And moreover, you can call it a proper Q coloring if you only are using Q different colors. This is an interesting graph theoretic question that, again, combinatorially explodes and that you often have to approximate. Okay, cool. Any questions based off of any of the preceding? Sweet. We can talk about Markov chains now, which are the real kind of difficult thing, I think, in this talk, but the main thing you need to talk about Markov Chain Monte Carlo. So we'll begin by talking about what a stochastic process is. A natural way to expand what random variables are is to think about random or stochastic processes. They refer to the same thing. And what these are is an indexed family of random variables. So if you write down, maybe I'll keep it over here like a word bank or something. But so we index random variable x with some index t, and t belongs to some like full family of, it's called an indexing set. So this is what defines a stochastic process. These can be distributed and related to each other in a whole lot of different ways. So you can pretty much arbitrarily relate all of the xt's to each other. They can be completely independent, like flipping a coin at each time instant, or they can be very related to each other. You can be ground in motion, you have a particle wandering, and so its current position does depend on its previous position. For example, a really popular subset of these, which I'm not going to talk about, I just think they look pretty and I wanted to shoehorn a graph of them in here, are Gaussian processes, where you make sure that any finite subcollection of these xt's is jointly Gaussian distributed. So, I don't know, hopefully other people find this pretty too. They end up very smooth depending on how you parameterize them and stuff. So now, one of the simplest ways we can think about relating all of these is to make a memoryless system. So it's hard to say. This is where the current system depends only on the previous instant. So this property of memorylessness is called the Markov property, which is much easier to say. It just says that the stochastic process at the next instant only depends on the current instant. For a discrete time process, we could write this down using some of the notation we have from before, where the probability of x of t, depending on all the previous states, is just equal to the probability of the current state given the previous state. In other words, if we have x1, x2, xn, the only thing that's relevant to predicting xn minus 1, or xn plus 1, sorry, the only thing that's relevant is xn. The rest of these do not give us any more information. So again, Brownian motion is probably the most famous example where we have some random walk of a particle, and where it goes next only depends on where it is now. You don't really care about where it started or where it was a second ago. You only care what the previous time instant was. So discrete time, if we have a stochastic process with a Markov property, we call it a Markov chain. Now, definitions of this actually vary a lot more than you'd think they would. Lots of subtle nuances to defining a Markov chain, but this is good enough for us. So if you have a stationary distribution, stationary meaning that how you change from one state to the next does not change over time, then the Markov chain x1 to x2 to and so on is described by a stochastic matrix S. Stochastic here means that the rows all add to 1. So for some properties, let's exposit a bit on what I mean by saying the stochastic matrix describes the Markov chain. And to do this, we can use some algebra. So if you have a hard problem, a nice way to think about it is always to translate it into some linear algebra and deal with those objects instead. So we do lots of algebra with this stochastic matrix X to learn about the system. So S is called a transition matrix, and so S has as its entries the probability of going from state 1 to state 1, probability of going from state 1 to state 2, and so on. And in general, Sij is equal to the probability of going from state I to state j. Does that make sense? Sweet. And then if we want to specify the probability over the current state, xt, as a vector, so I'm just writing down the probability that x is in state 1, probability that x is in state 2, all the way to probability that x is in state m, then going to the next state is described by just right multiplying by the transition matrix. So just to write it down, as an example, if xt is definitely in state 1, we have a stochastic matrix over here, then the result is just this row, right? We evolve from state 1 to this probability distribution right after, by right multiplying by S. More generally, we can just think about matrix multiplication and then just exponentiate it. So if we wanted to go 2 states into the future instead of 1 state, well, we can take p of x t times s. So this whole thing is p x t plus 1. And then we multiply this whole thing by s again to get p of xt plus 2. In general, we could just multiply by s n times and get the probability distribution n seconds or time units into the future. Cool. Any questions on? Sweet. So there's some pathologies if we want to talk about Markov chains, things that make them kind of uninteresting in a lot of ways. And for a starting point, we should be able to get to any other point, right? So if you start in state 1, it's kind of useless, or it's kind of weird if you cannot access state n, right? There should be some path to go from one to another. This is the idea behind irreducibility. So a Markov chain is irreducible if it can be broken down into finite paths if you always have some sort of way to cycle. So one easy way to have this, one way that is probably the most interesting or the most common, is for each entry of Sn to be greater than 0 for some n. The accessible states should also not depend on n if sufficiently large. So an easy example here would be if even states were only accessible on even time instances, and odd states were only accessible at odd time instances. This is a kind of pathology if we want to talk about the distribution after a long period of time. Right? You should want this distribution to not change its support over time. This is captured in a property called aperiodicity. The periodicity says that the Markov chain has some place in time where it cannot access all of the states. If the chain is irreducible and aperiodic, oops, looks like I forgot to finish the sentence there. But I think what I was going to say is that if a chain is irreducible and aperiodic, then we have that any state is attainable after any state is attainable after a sufficiently long time from any starting point. This ends up being sort of a sufficient condition for lots of the things that we're interested in. So then we can talk about what stationary distributions are and use a little simulation that I wrote. The idea is that if we start off with some initial distribution in our Markov chain, and then we let it evolve over time, then after a while, we might expect that it reaches a point where the distribution does not change. So I could run this little simulation again, and the point is that we start off at some initialization, and then over time, the amount that, or the number of times that the state is any one of these three sort of levels off. These circles don't really change shape much after a few iterations. So in order to do this, we have that from before that p of t plus n is equal to p of t times the transition matrix exponentiated. And then we could ask what happens in the limit as n goes to infinity. If a limit exists, then pi of x has to be equal to pi of x times s. This is because essentially what we want the limit of pxt times s. And this shouldn't, so right multiplying by this to go to n plus 1 shouldn't change a whole lot, right? The distribution should stay the same if this limit exists. It therefore doesn't always exist, right? It might be the case that s is not the same there's no probability vector such that multiplying by s keeps it the same. This is usually some pathological Markov chain like we talked about before. But we can play with some numbers. For example, running a simulation like this one and seeing that it sometimes does exist, and actually quite often exists if you have a sufficiently nice Markov chain. So we can talk about a definition of stationary distributions now. So this property over here, or on the last slide rather, that it stays the same after right multiplying, makes it a stationary distribution. Some stationary distribution exists and is unique, basically if the pathologies we talked about before don't exist. If it's finite, irreducible, and aperiodic. I should mention that the infinite case is a little bit harder. You end up talking about things like Harris recurrence or other confusing words. But in the finite case, the irreducibility and the aperiodicity is enough. Furthermore, under these conditions, the finite, irreducible, and aperiodic, no matter what the initial distribution was, will converge to the stationary distribution. So we can start in any given initialization, and then if we take a limit as n goes to infinity, the evolved system will follow the stationary distribution. So this is in the sense that there's a few different senses you could write this in. One of them is that the probability of xt converges to pi of x, the stationary distribution, in a total variation sense. This is essentially there's some distance given by a difference in integral. Any questions off of stationary distributions? Okay. So one way to show that a distribution is stationary, and one that will end up being quite convenient later, is saying that it satisfies the detailed balance equations. So I'll write this down. So the detailed balance equation says that the distribution, or the probability distribution on x times the transition matrix to go from x to y is equal to probability on y times the transition from y to x. This is really a statement dynamically about the process being in equilibrium. It's equally likely to go from x to y as it is to go from y to x. Detailed balance, again, will be the key thing that we exploit later on when we want to write down the Metropolis algorithm. Okay, cool. Doing good on time, I think. So Metropolis-Hastings is, again, probably my favorite algorithm in all of statistical computing, and really is a really clever trick that I struggled to comprehend for a while. So excited to talk about it. If we're going to talk about Markov Chain Monte Carlo, we should talk about the latter part first, the Monte Carlo. So Monte Carlo is, of course, a city in Monaco. It's famous for its casinos. But also, like I alluded to before, Monte Carlo was a code name because they came up with these algorithms at Los Alamos during World War II. And so they couldn't really say a whole lot about what they were working on. So a few years before the Metropolis algorithm, which is in 1953, Monte Carlo, or in its modern form, was born. Stanislas Ulam was thinking about combinatorially intractable problems, like we were talking about before. So for example, winning hands of solitaire just blows up too quickly, and you can't write it down analytically. And John von Neumann adopted this method for statistical physics, like they were doing at Los Alamos. People always use like a weird picture of John von Neumann when he was old. I thought this one was cute. It was on Wikipedia. But anyways, if we want to use random, the idea behind Monte Carlo is we want to use random samples, and then kind of take that gamble that the answer is close to the real analytic one. So the core idea is that if we can't do integrals by hand, we should approximate them using finite samples. So if we have samples x1 to t, and they're distributed according to p of x, then we want to approximate the expected value of h of x by its value on some finite sample. Now a picture for this looks something like this. We have some distribution over here. The integral is some area under this curve, right? Instead, what we're going to do is we take a bunch of finite samples. So you say that these should happen approximately this often, right? So maybe it's a little bit above or a little bit below, but if you take enough samples, you end up looking like the distribution, and then you take a finite sum instead of the integral. So just like you learn in like a Calc 1 class, where you have an integral in terms of a Riemann sum, Similar idea. We break down the domain and then approximate the integral with a really fine mesh sum instead. Does this sound good? Cool. The core problem, however, is that, that should be P of x, sorry. The core problem is that getting these samples is really hard. It's not obvious. There's a lot of methods, but there's issues with each of them. So you could take the inverse of the CDF, which I didn't talk about CDFs, but this is a popular method. It's really difficult to do. You can do this thing for really simple random variables, like a beta random variable, but doing it for things that are non-trivial is pretty much impossible. You can do something called accept-reject methods, of which we're actually going to do a form of, but in their naive form, these require some really weird guess, otherwise you have lots of bias. And then there's importance sampling, which is actually a pretty good family of methods. It's the main competitor to Markov Chain Monte Carlo methods. But these have large variance if you're not very careful. You really have to use good methods and use good math in order for these to not blow up. So then the idea for Metropolis is, can we use Markov chains to do this sampling? The crux of MCMC is this sort of inverse problem as a result. So given some arbitrary distribution, pi, so this is called the target distribution now, does a Markov chain, the stationary distribution pi, exist? So there's two reasons why this is like, where you should trivially be saying yes. Does anybody have either of them? Okay, so the first one is we could just choose a Markov chain with the distributions. This is kind of like tautological and not really helpful. The other reason why you should think that there definitely exists a nice method to do this is because this is a talk about Markov Chain Monte Carlo, and so, of course, if I'm talking about it, it does exist. So as a note, we'll formally state things here in terms of finite sample space Markov chains, just because everything works out nicer. The theorems that we did before were irreducibility and aperiodicity were enough. Make this case very much easier, but the general algorithms hold and are largely the same in the infinite case. And so the main takeaways here and the algorithms that we write down hold in much more general circumstances. So detail balance before was something that we said was going to make things much easier as we went on. How do we make this method useful? Well, what we do is we sample from some distribution that's somehow wrong, but easier to sample from. So for example, we know how to sample from a normal distribution. And then we have to correct the samples by accepting or rejecting them. So we can sample from a normal distribution and then later adapt these samples in order to conform to our target. So we'll start with the proposal of Metropolis, in which case the proposal is symmetric. So again, this normal case is a case where it's symmetric. You have a certain point of your stochastic system, and you're equally likely to go up or down or left or right. And this makes the math a whole lot easier as well. So we want to find acceptance probabilities, AXY and AYX, such that detailed balance holds. This would say, so if SXY is equal to psi xy times AXY, then if this equation holds, detailed balance holds, and pi is the stationary distribution. Since x is symmetric, we can drop the pi xy terms on each side of the equation, and we end up with a simpler equation that p of x times axy is equal to pi of y times ayx. Moreover, we'd want to, sorry, that should be maximizing AXY, not maximizing pi times AXY. We want to maximize the acceptance probabilities. It's very wasteful to reject samples. We want to take advantage of every step on a computer that we do. If we do this maximization, so if we satisfy detail balance and maximize the acceptance probabilities, we end up with this transition matrix. So the transition from state x to state y is given by a symmetric proposal that's easy to sample from, times an acceptance probability that's easy to calculate. In the case x is not equal to y, or just some finite complement otherwise. So we can leave this up to simmer for a second. It looks kind of complicated, but the main idea is that we sample from some easy to sample thing, and then you just scale it by a number that's pretty easy to find. Any questions on this? Cool. So now Hastings in 1970 generalized this result. There's not really any good pictures of Hastings. I don't know if he was really famous for this and not really famous for anything else. But in Hastings' generalization, we can include cases where the proposal distribution is not symmetric. This is really important for things like random walks, where you might want to take into account that going from one state to the other near a boundary is not symmetric. This is pretty much the same. The derivation is a little bit harder to maximize given the detailed balance is satisfied, but the algorithm itself looks very similar and it's pretty simple to verify just given some simple pushing that detailed balance holds. So in this case, the transition matrix looks quite similar. We take some proposal from x to y, and then we minimize some acceptance, or we take the minimum of 1 and some acceptance probability that is slightly messier, but not so messy. Then we want to use Metropolis-Hastings. Using the findings of Metropolis in Hastings, we can sample some very difficult probability distributions that we just had no idea how to use otherwise. Now, one thing to note that's really convenient is that Metropolis-Hastings only relies on the ratio of pi x to pi y. So I can show why this is really awesome and relevant. So before we had so we wanted a sample from this. Now this thing was really difficult, right? However, if we have ratios, so theta 1 given x over p of theta 2 given x, then these px's cancel out. We're taking a ratio where px is common, doesn't depend on theta, and so this is p x given theta 1, p x given, or p of theta 1 over same thing with theta 2. The p of x is canceled out. We don't actually need to calculate them, which would have been a nightmare. Same idea in the statistical mechanics example. So in the stat mech example, we had that p of sigma is the exp of negative beta times the energy over some terrible constant z. Well, we don't have to calculate the terrible constant anymore. If we want to go from sigma 1 to sigma 2, again, z cancels out as it's a ratio of the two. So this is awesome for us. We don't have to calculate these terrible things in order to use our methods. However, as Rick stated so far, we're only taking individual samples from the end of a Markov chain. So we're simulating a Markov chain for a long time and then only using the last sample, which seems pretty wasteful. And that's the only way that what we've talked about so far actually works. The individual samples tend to be really correlated to each other because of your proposal distribution. So how do we use the entire Markov chain instead of just the last sample? This is the last slide. We want to use the whole thing, but there's a lot of correlation. But fortunately, under some, again, mild conditions, we can still sum everything together. It still works. We can use the entire Markov chain. We can use every single sample that we took. And this is a Markov chain central limit theorem. So some of you might have heard of central limit theorem in a statistics class or in a physics class or something. And it turns out that for a Markov chain, we can do this. So if you have a stationary distribution pi x, and gx is some function with finite variance, then as we take the limit, this approximation, the Monte Carlo approximation, holds. And it scales, the standard deviation scales with square root t. And the sigma is just a constant that depends on the variance of g and the autocorrelation. So that's all I have. This is a pretty picture of a Markov chain. Starting with Wikipedia, we're just doing a cool distribution. So you can see that you simulate a Markov chain, starts from a really weird place and then traverses to a more sensible place. Cool. Thanks. Any questions?
I have a question, but I actually don't know enough to actually ask it. So in lecture today, they did something called teacher talked about something called the Frobenius operator. Do you know that that's related to Markov chains?
I mean, it can be. It's not really like in the MCMC part, but Frobenius operators are important if you want to study dynamics. And if you want, I can send you some stuff about it. So like, there's stuff like Frobenius. There's a great book by Alyssa and Mackie that's really popular.
Thank you.